Hi everyone, welcome to our channel. Today's our topic is about quantum numbers. There are four types of quantum numbers. Before discussing about these quantum numbers, first of all, what are the quantum numbers? Let we discuss. Quantum numbers describe the exact position of electron inside the atom. Means where the electron is inside the atom. We know that electrons are inside the atom and moving around the nucleus in different paths which are known as orbits or shells, as we discussed in the previous class. Whereas the electron is revolving in a particular orbit, its location, exact location, how can we predict the exact location of the electron? Because electron is a microscopic particle and which is not stable in one place. It will always moving from one place to another place inside the atom, and they are high energetic, and it is impossible to find electrons simultaneously. It is impossible to predict the location and velocity of electron at the same time. This was told by Heisenberg. Heisenberg uncertainty principle tells that it is difficult to find the exact location and momentum of the electron at the same time. So as per that, to know the electron and approximate position of the electron inside the atom, we have four quantum numbers to locate the electrons. They are: first one, principal quantum number; second one, azimuthal quantum number or angular momentum quantum number; third one, magnetic quantum number; fourth one, spin quantum number. So let's discuss one by one all types of quantum numbers. Principal quantum number. So this quantum number tells about the, suppose this is the nucleus and electrons are revolving around this nucleus in these specified paths. This principal quantum number tells about in which orbit the electron is, in which orbit the electron present, orbit number. So these orbit numbers, as we discussed in the Bohr's atomic model, these orbit numbers are n equal to 1, 2, 3, so on, or they are designated with K, L, M, N, so on. Okay, so now let us discuss how this principal quantum number uh, can be useful in finding the energy and position of the electron. Let me see first principal quantum number proposed by the scientist Niels Bohr. It is proposed by the scientist Niels Bohr, and this quantum number is represented by the letter small n, and third thing about principal quantum number is its values are n equal to 1, 2, 3, so on, or K, L, M, N, so on. And finally, it is used to know the size and energy, of stationary orbit. Stationary orbit. So these are the 4 points related to principal quantum number. Means if electron is there, for example, any electron is given, so it is belongs to which orbit and orbit number, its values. By knowing this orbit number, we can estimate the size and energy of the stationary orbit. Suppose if n equal to 1, it is very near to the nucleus, and n equal to 4, it is far away from the nucleus, and if n equal to 1, it is less energetic, and if n equal to 4, it is more energetic. Like that, it is used to know the size and energy of the stationary orbit. Angular momentum quantum number or azimuthal quantum number. Suppose we know, before we discussed that in each and every atom, electrons are revolving around the nucleus in a specified paths called orbits or shells. From the principal quantum number, we know that orbit numbers n equal to 1, n equal to 2, n equal to 3, and n equal to 4. These are principal quantum numbers. And in each shell, as per the Zeeman effect, what we know, each spectral line is splitting into sublines due to each stationary orbit is dividing into some substationary levels. So each stationary orbit dividing into some substationary by seeing like this. In first orbit n equal to 1, only one sublevel is there, that is 1s. And in second orbit n equal to 2, two sublevels, 2s and 2p. And third orbit, three sublevels. Fourth orbit, four sublevels. So nth orbit is having n sublevels or subenergy levels or suborbits. So let us discuss one by one. So what are the various subshells in the orbit? In first orbit, K shell, only 1s is the subshell. In L shell, 2s and 2p are the subshells. In M shell, 3s and 3p, 3d are the subshells. In N shell, 4s, 4p, 4d, 4f. So s orbital, these are also called as orbitals. S orbital, s and p orbitals, s p d orbitals, s p d f orbitals. So f orbital starts from fourth shell only, means n shell. N shell onwards, f orbitals will start. Before n, no f orbitals. So in first shell s only there, in second shell s and p, in third shell spd, in fourth shell spdf. This s orbital is there in all shells, but in first orbit s orbital is 1s, in second orbit s orbital is 2s, in third orbit s orbital is 3s, in fourth orbit s orbital is 4s. Likewise, p orbital starts from second shell, 2p, 3p and 4p, 3d and 4d, next 5d also, 4f, and next 5f and 6f, like that. So like this. So from this we know one more thing. For SR, let we discuss first quantum number, angular momentum quantum number. This is discovered by the scientist Sommerfeld. Sommerfeld. And it is proposed by Sommerfeld, and it is represented with the letter small l. Its values are l equal to 0, 1, 2 until n minus 1. Suppose n equal to 4, its values are up to 3 only. And next, fourth, it is used to know the shape of the subshell. Shape of the subshell. Let we discuss about this. So these are the 4 points regarding angular momentum quantum number. Scientist name Sommerfeld, represented by the letter L. Its values are L equal to 1, 2, 3, 4, so on up to n minus 1. Shape of the subshell. Okay. So s orbital is having L value 0. L value 0. P orbital is having L value 1. D orbital is having L value 2. F orbital is having L value 3. Angular momentum quantum number is 3. For example, here in first orbital only s is there. In first orbit only s orbital is there. S L value 0. N equal to 1, L value 0. Means n, for n equal to 1, L value 0. For n equal to 2, 0 and 1. 0 and 1. For n equal to 2, 0 and 1. For n equal to 3, 0, 1, 2. For n equal to 4, 0, 1, 2, 3. Means up to n minus 1 only the values will end. Okay, let's see. Let's see here. This is principal quantum number, and this angular momentum quantum numbers, how will be? Let we discuss. For n equal to 1, so L values are 0. For n equal to 2, L values are 1, 0, 1. For n equal to 3, L values are 0, 1, 2. For n equal to 4, L values are 0, 1, 2, 3. N equal to 4, 4 values are there, but up to 3 only, n minus 1. And what are the orbitals we have? L equal to 0 means only S. This first shell, no, that's why 1s. In second shell, S and P. Second shell, no, 2s, 2p. Here, S, P, D. 3s, 3p, 3d. S, P, D, F. 4s, 4p, 4d, 4f. So like this, we can discuss about the angular momentum quantum numbers.